So let's now talk about dot products. I have a vector A, ax times x roof, which is the unit vector in the x direction, plus ay y roof, plus az z roof. So these are the three unit vectors in the x, y, and z direction, and these are the x component, y, and the z component of the vector A. I have another vector B, B of x, x roof, B of y, y roof, B of z, z roof. Now the dot product, A dot B, also called the scalar product, is the same as B dot A, and it is defined as AX BX plus AY BY plus AZ B of Z. It is a number. It is a scalar, it is a simple number. And so this number can be larger than 0, can be positive, it can be equal to 0, it can also be smaller than 0. They're just dumb numbers. There is another way that you can define, you can call this method number 1 if you prefer that. There is another way that you can find the dot product which gives you exactly the same result. If you have a vector A and you have the vector B and the angle between them is theta, then you can project B on A, or A on B for that matter, it makes no difference. And that projection, the length of this projection is then of course B cosine theta. And so A dot B, and that is exactly the same. You may want to go through a proof of that. It is the length of A times the length of B times cosine of theta. And that will give you precisely the same result. What is interesting about this formulation, which this lacks, that you can immediately see that if the two are at 90-degree angles, or 270 degrees for that matter, then the dot product is 0. So that's an insight that you get through this one, which you lack through that other method. Let us take a down-to-earth example of a dot product. Suppose A equals 3x and B equals 2x plus 2y. And I'm asking you, what is the dot product? Well, you could use method number 1, which in this case is by far the fastest, believe me. AX is 3 and BX is 2, so that gives me a 6. There is no AY, there is no AZ, so that's the answer. It's just 6. That's the dot product. You could have done it that way. It's a little bit more complicated, but I certainly want to show you that it works. If this is the x direction, and this is the y direction, we don't have to look into the z direction because there is no z component, then this would be vector A, and this point would be at 3. B, this would be 2, and this would be 2, and so this would be the vector B. And it's immediately clear now that this angle is 45 degrees. That follows from the 2 and the 2. So if we now apply method number 2, A dot B, first the length of A, that's 3, times the length of B, that is 2 times the square root of 2. This is 2, this is 2, this is 2 square root 2, times the cosine of 45 degrees, which is 1/2 square root 2, and the answer is 6. Notice that this square root of 2 and this square root of 2 eat up this 2, and you get 6. You get the same answer, of course. But it would be a dumb thing to do it, since it can be done so much easier. On cross products, I don't want to go through the formalism of cross products the way we did that with the determinant. I just want to remind you that if you have a cross product of two vectors, that is minus B cross A, and that the magnitude of C is the length of A times the length of B times the sine of the angle between them. The vector C, the dot product, the cross product, is always perpendicular to both A and perpendicular to B. In other words, it's perpendicular to the plane of the two vectors. Now, if it's perpendicular to the plane, then in that case, it's perpendicular to the blackboard. You have two choices. It's either coming at you perpendicular, or it's coming straight into the blackboard. And now, everyone has his own way of doing it. I taught you what's called the right-hand corkscrew rule. You take the first one that is mentioned, in this case A, and you rotate it over the shortest angle to B. When you do that, you rotate your corkscrew, seen from where you're sitting, counterclockwise. Then the corkscrew comes to you, and so the direction of the vector is such that you will see the tip of the vector, so it's coming straight out of the blackboard. And so that gives you then the direction.